In this lesson, we're going to be talking about I'm going to show you how to basically determine the empirical formula as well as the molecular formula. So there are two types, empirical as well as molecular. And by the end of this lesson, you're actually going to be able to distinguish between these two types of formulas and how to find each, right? So, I think it's just a good idea to start off by actually doing a calculation. So, just to start with a working definition, empirical formula is defined as the chemical formula of a compound that shows the smallest whole number ratio of the reactants. So all that definition will make sense after we've actually calculated both the empirical as well as the molecular formula. Cool. So let us just start with this example over here. So they're saying to us that 207 grams of lead combines with oxygen to form 230 grams of lead oxide. Cool. But I use this information to work out the empirical formula of the lead oxide, right? And now they have given us the molar mass of each of for both lead as well as oxygen. So you can find these values on your periodic table by looking at your atomic mass, right? Cool. So how do we start off? How do we go about doing this calculation? So one thing that we are sure of is that this reaction we have oxygen, or we have lead that is reacting with oxygen, right? And then as a result, it gives us lead oxide, right? So they've given us the value for lead, the mass value, and they said that I'm just gonna write there at the bottom. So the mass of that is 207 grams, and then we don't know what the mass of oxygen is. However, they've given us the mass of lead oxide, which is 230 grams. So remember, there's an important thing when it comes to chemical equations or balancing chemical equations, and that is this important law of conservation of mass. So the mass on your left hand side should actually be equal to the mass on your right hand side. That is very important for you to be able to know and understand. So meaning to find the mass of oxygen, I can simply say it's going to be, so to find the mass of oxygen, so M oxygen is just going to be 230 grams, and you'll see why I'm looking for the mass of oxygen. 230 grams minus 207 of the lead, right? And I think the value that you come to is about 32 grams. You can always check these answers with me on your calculator, right? So now we have the value for 32 grams. So 207 grams of lead reacts with 32 grams of oxygen to essentially produce 230 grams of lead oxide. So now for our second step, and to do this, I normally like drawing a table. So the table that I draw, this is a way to just calculate the, what is it that we're looking for, the empirical formula. So because we have two reactants, so our table will only be like 3 columns. So let me just draw the first column and this third, second and third, right? And then on this part of here, I'll write lead, one of our reactants, and then on this side I'll write oxygen at the top there. And then I'll say here on this row, you write the mass of the element. Mass of the element, we know it's measured in grams. And then here, it will just be the number of moles. Remember, equation for our number of moles is M, small m, divided by big M. And then finally, here, I'll just write atom ratio. And you'll see what that is shortly. Cool, right? So we've done, so we know the mass of lead, it was 207. We know the mass of oxygen. We calculated it, that's why we calculated it, and we found it to be 32 grams. Remember, it's measured in, this is measured in moles, right? Now, how do we find the number of moles? You know, to find the number of moles, I must simply divide the mass by the molar mass. So they gave us the molar mass of lead to be 207. So N here, it's 207 the mass divided by 207 comma 2, which if you round it off will just be 1 mole. Cool. We do the same thing for oxygen, and it's just going to be 32 divided by the molar mass of oxygen, which was 16. They gave it to us, but you can also just look for it, determine it using your periodic table by looking at the atomic mass, right? So 32 divided by 16, we know it is 2, so meaning it's 2 moles of oxygen. And now to find the atom ratio, we're gonna say that we're gonna divide each of these moles. So first determine which is the smallest mole between these two. Between 1 and 2, definitely it's 1, right? And we divide each of these moles by the smallest number of moles. So we'll have, for this one, we'll have 1 divided by 1, right? Which will give us 1. And then in this instance, we have 2 divided by the smallest one mole, which is 1, right? So this is 2. So what is this telling us? This is telling us that the ratio of lead to oxygen is nothing else but 1:2. So meaning for every one I don't know, one atom of lead, we have 2 of, what is this thing? Oxygen, right? So meaning its empirical formula is simply be Pb. We don't need to write the 1O2. So now we have found the empirical formula of lead oxide. Let's just do another way of finding the empirical formula when we given a percentage composition. So in this instance, we were given the mass, but what about in terms of when we are given the percentage? Pretty much the same process, right? But you'll see that our initial step, how do we convert from that percentage to mass, which is a very critical step. Okay, so this is another what is this question that we can actually look at, and it says to us that a sample of acetic acid has the following composition. So the 9.9% of that is carbon. I'm lying. And then what is it? 6.7% of that sample is hydrogen, and 53.4% of that is oxygen. So when in terms of percentage composition, always make sure that all of this what is this? All of these percentages for the individual elements in the sample actually add up to 100%. So you'd have 39, so we'd have 39.9 plus 6.7 plus 52.4, which will give us 100%. So what does this imply? This implies that if we had a sample of 100 grams, so if we had a sample of 100 grams, it means that so the mass of carbon in that sample would be 39.9 grams, right? And then the mass of, what's the other one? Hydrogen, let me just write H, would be 53.4 grams. And then the mass of, what's the other thing? Oxygen would be, how much is this? Ooh, I am lying. So this is 6.7 grams, right? And then finally oxygen will be 53.4 grams. Cool. And now we now have the masses. It's just the same process that we did earlier in terms of finding the, I don't know why I'm forgetful, in terms of finding the empirical formula. So let us just do the same thing. So we'll draw those tables of ours. So as I had done the other time, I just drew a table. In this column, I wrote carbon at the top, hydrogen, oxygen, and then here will be the mass, the number of moles, as well as the atomic ratio. So the mass of carbon, we said it is 39.9 the mass of hydrogen is 6.7, and then the mass of oxygen is 53.4. So to find the number of moles of carbon, we simply say its mass, which is 39.9 divided by 12. And a value that you'll find there, you can just round it off to, okay, you don't need to round it off actually. Why am I lying? Okay, so somebody knocked on my office door. I don't actually remember where was I. So we had, hopefully, so I was here. So where we say 39.9 divided by 12, and it's going to give us, let me just remove this, and it's going to give us 3,325 moles, right? So this is measured in moles. And then you can do the same thing for oxygen. We have 6.7 divided, this is hydrogen, divided by its molar mass of 1.01. Let me check this. Trying to check my periodic table. It's 1.01 or 1. So you find that the value that you find there is, how much is that? 6.6337. Same thing for oxygen, 53.4 divided by 16, which will give us 3,3375. And now we have to divide by the smallest mole there. So the smallest is 3.325. So meaning we'll have 3.325 divided by 3.325, which will give us 1. And then 6.6337 divided by 3.325 is going to give us, if you round it off, it will give us more or less 2, right? You round it off to the nearest whole number. And then here 3,3375 divided by 3,325, rounded off to the nearest whole number, it's going to be 1. So what is that implying? That is implying that the ratio of, let me write it on the other board. So this is implying that the ratio of carbon to hydrogen to oxygen is 1 is to 2 is to 1. This marker is so stubborn to wipe off. That's why I don't like using it. 1 is to 2 is to 1. Meaning the empirical formula will be CH2O. So that is our empirical formula. And remember, how is it that we defined our empirical formula? We said that the empirical formula of a compound shows the smallest whole number ratio of atoms. So now I want us to move our discussion to molecular formula. So when we talk about the molecular formula, let us say we had the same question, such as this one. Let me just remove this. And so we had the same question. So we found our empirical formula as C8, right? CH2O. So that's it, the empirical formula. So now let us say the question continued to say that. So let us say that the question continued to say, determine the molecular formula. Determine the molecular formula of acetic acid if the molar mass of the acid is 60.06 grams per mole, right? So they've given us the molar mass of acetic acid. Let me just put this here. So how do we go about this? So the first thing is that we have found the empirical formula to be this way. And from this empirical formula, we can determine the molar mass, M. And to find that, we'll simply say carbon 12 plus 1.01 multiplied by 2. So that's the molar mass of hydrogen times 2 plus 16 molar mass of oxygen. and that entire thing is going to give us 30.2 grams. But now you're noticing something. The molar mass that we're calculating from the empirical formula is 30.02. The molar mass that they gave us was, which is the right molar mass, or the actual molar mass of acetic acid, is 60.06. And to find the molecular formula, we have to say, okay, let us say the actual molar mass of whatever substance we're dealing with divided by the empirical molar mass. So the actual molar mass is 60.06, and if we divide that by the empirical one, it's 30.2. And that, if you round it off to the nearest whole number, is going to give us 2. So meaning we have to double everything in our empirical formula. So meaning that our molecular formula, molecular formula, I don't know why I had to write this, is going to be C2, and then H2 times 2 is 4. So it's going to be H4, and then oxygen O2. So this is actually our molecular formula. So now differentiate between what is it, empirical formula and molecular formula. For empirical formula, we get the smallest whole number ratio of the atoms, and here is not really the smallest whole number ratio of the atoms. That is the actual molecular formula. And yeah, I think in terms of this lesson, we are actually done. Let me see. Yeah, we are done.